The next mode of heat transfer is convection. This is the most complex heat transfer mode among the three, and we will explain why in future lectures. As what we have previously said, convection occurs at the surface of a material. Mostly this material is a solid, but in some instances, this can also be a liquid. Now heat is transferred from this surface by convection if there is a fluid motion adjacent to this surface. Just like in conduction, there are also two mechanisms by which convection occurs: conduction and advection. Now, it can be quite confusing to think that conduction is a big part of how convection happens, but let me explain this using an example. Let's say we have a hot light bulb in a relatively cold room. We can see from this diagram that cold room air moves upward once it is heated by the surface of the light bulb. If we zoom in to the surface of the light bulb, we will see that there is a portion of the airflow that is directly affected by the presence of the hot light bulb. This portion of the airflow is represented by a temperature gradient and a velocity gradient in the air. This portion is called the boundary layer. Now, where can we see the two convection mechanisms in this example? If we zoom in closer to the surface of the light bulb, we will see that some of the air particles are not moving. This is caused by the frictional force exerted by the light bulb surface in the movement of the air. The presence of a very thin layer of motionless air at the surface of the bulb allows heat conduction to occur through this layer. Now, advection occurs at the portion of the boundary layer in which air is already moving. Advection pertains to heat transfer from a surface solely due to the bulk motion of the fluid. Now that we have discussed how heat convection occurs, let us now tackle how to compute for the rate of heat transfer from a surface. Newton's law of cooling is the principle governing the convection process. This law states that the rate of heat convection is directly proportional to the surface area and to the temperature difference between the surface and the surrounding fluid. It must be stressed that the free stream temperature, T sub infinity, is measured at the portion of the fluid flow which is unaffected by the presence of the surface. The proportionality constant that we use in turning this proportionality statement into an equation pertains to the convection heat transfer coefficient. This is denoted by small letter h. Another term pertaining to convection heat transfer coefficient is film conductance. Now it must be stressed that unlike thermal conductivity, film conductance is not solely a fluid property. Its magnitude depends on several factors, such as the shape of the surface from or to which convection occurs, the nature of flow, the velocity of the fluid itself, and lastly, the fluid properties. This is the reason why, when you see a table of convection heat transfer coefficients such as this, you must understand that the values in this table are just average values. In fact, one of the most challenging aspects of dealing with convection problems is determining the value of the convection heat transfer coefficient. Now, there are several convection heat transfer processes. The first is forced convection. This is a type of convection in which we force fluid to flow through a surface using external means, such as blowers or fans. When you try to cool down a very hot soup by blowing, what occurs is forced convection. The second is free or natural convection. This is a type of convection which occurs when fluid flows through a surface due to buoyancy, and no external means are used to force fluid flow. A very common example of this is when we allow hot coffee to cool down inside a relatively cooler room. The last two convection heat transfer processes are also very common: boiling and condensation. We will be discussing the mechanisms behind each of these processes in future lectures.